We'll tackle the two examples here. First, to talk about this property of radicals that we've mentioned in passing but maybe haven't looked at in detail, and also to introduce the idea of rationalizing denominators. We could just as well rationalize numerators, but we're asked here to simplify by rationalizing the denominator. What does that mean? That just means to remove the radicals from the denominator. I'd like to re-express this fraction in such a way that it only has integers in the denominator. Okay, how do we do that? Well, as long as we do the same thing, multiplication or division only, to the top and the bottom of the fraction, we can multiply by whatever we'd like. What would we need to multiply the square root of 3 by in order to turn it into an integer, to remove the radical? Well, the square root of 3 times the square root of 3 is just 3. So in order to rewrite this fraction, I'm going to multiply the bottom by the square root of 3, and therefore also the top by the square root of 3. Multiplying fractions is pretty straightforward. Multiply your numerators, multiply your denominators. The square root of 2 times the square root of 3 gives me the square root of 6, and the square root of 3 times the square root of 3, of course, gives me just the square root of 3. Since the 6 is under a radical and the 3 isn't, we can't do any division here, and this is the final expression of that fraction. The second question allows us to also talk about the property of radicals that I've highlighted on the right here. If I have the square root of 11 over 12, remember that I can write that as 11 over 12, all raised to the power of 1/2. What do we do when we have a quotient raised to an exponent? Well, we raise the numerator to that exponent as well as the denominator. In other words, we take 11 and raise it to the 1/2, which is the square root of 11. We take the 12 and we raise it to the 1/2, which gives us the square root of 12. So that's where this property comes from. It's not unique to radicals. It's derived from the fact that radicals can be written as fractional exponents. So anytime we see a radical that looks like this, we can go directly to this depiction. Now you can do two things. You can either go ahead and simplify the square root of 12, because I can see that I'm going to simplify that, or I could go ahead and multiply the top and the bottom of this fraction by the square root of 12. In this case, I'm going to simplify the square root of 12. So it won't touch the square root of 11, but since 12 can be written as this, so square root of 12 can be written as 4 times 3 under the radical, it will simplify to 2 root 3. So we'll have 2 root 3. The only radical in the denominator is the root 3, so now I'm going to multiply top and bottom by the square root of 3. If you went ahead and multiplied the original by root 12 over root 12, don't worry, we'll end up at the same answer. The square root of 11 times the square root of 3 is the square root of 33, and in the denominator I have 2 times the square root of 3 times the square root of 3, or just 2 times 3. So our final answer is the square root of 33 divided by 6. These questions are the main event. We're looking to rationalize the denominators in these slightly more complicated fractions. We're going to use the same principle that we used when the denominators were just monomials, single radicals. We're going to multiply the denominator and the numerator by the same thing, because of course we can only multiply a fraction by 1, otherwise we change its value. And the goal here is only to rewrite the fraction so that there are no longer any radicals in the denominator. We could, again, rationalize the numerator if that was the instruction, but we want to do so without changing the value of the fraction. All right, so let's multiply top and bottom by what's in the denominator. I definitely want to use the positive 2 root 15 and also the square root of 5. However, the only way that I'm going to eliminate my radicals is if I change the middle sign. So because the middle sign here is negative, I'm going to change it to positive. We call these two conjugates. 2 root 15 minus root 5 is the conjugate of 2 root 15 plus root 5. Only the middle sign will change, even if there's a negative sign in the first term. If I'm going to multiply the bottom by 2 root 15 plus root 5, I'd better multiply the top by exactly the same thing. I find it helpful to put this in brackets so I can see that I'm just doing the multiplication of two binomials in the numerator and the multiplication of two binomials in the denominator. So let's do that. So first we take the square root of 15 and multiply that by 2 root 15. So we have 1 times 2 is 2, and root 15 times root 15 is just 15. For this example, I'm going to speed up the process of multiplication a little bit. And we take the square root of 15 and multiply it by the square root of 5. Square root of 15 times the square root of 5, they're both positive, so we'll have positive 15 times 5, or positive root 75. Now we'll take negative 3 root 5 and multiply it by both terms in the numerator as well, in the second binomial of the numerator. Negative 3 root 5 times 2 root 15, that will be negative 3 times 2 is 6, 5 times 15 is 75. And finally, negative 3 root 5 times root 5 is going to be negative 3 times 5. That's just our numerator. So now we need to do the same thing for the denominator, multiplying binomial times binomial. So we start with 2 root 15. 2 root 15 times 2 root 15. That gives me 4 times 15. 2 root 15 times root 5 is, that gives me positive 2 root 75. Here's where it starts to get interesting. Now I'm going to take negative root 5 and multiply that by 2 root 15. So that's negative 2 root 75. And then finally, negative root 5 times positive root 5 is going to be negative 5. The reason this is interesting is because the middle two terms in the denominator cancel each other out. Our first term is just going to be 4 times 5 is 20. Our last term is also just a number. We're going to subtract 5. And the middle two terms are identical, except that they have opposite sign. This happens because we used conjugates, because we changed the sign so that we multiplied by 2 root 15 plus root 5, where there was initially a negative sign in our question. As long as we change that sign, we're always going to have this situation where the first and the last term eliminate the radicals, and we will have some values left. And the middle terms will cancel each other out. Now all we need to do is simplify numerator and denominator. So in the numerator, 2 times 15 is 30. Positive root 75 minus 6 root 75 is minus 5 root 75. And minus 3 times 5 is negative 15. You can see that we can tidy that up a little bit further before we're done with it. In the denominator, 4 times 5 is 20. The middle two terms cancel, and we're left with 20 minus 5. A couple things left to do. We have to do the subtraction given by the numbers, and we'll have to simplify the square root of 75. We can do that in 2 more steps. 30 minus 15 is just 15. And here we have negative 5 times, well, I'll do the simplification of the square root of 75 over on the side. That's going to be 25 times 3. The perfect square that is a factor of 75 is 25. The square root of 25 is 5, so the square root of 75 simplifies to 5 root 3.
All right, the negative 5 root 75 therefore becomes negative 5 times 5 root 3. So finally we have 15 minus 5 times 5 is 25 minus 25 root 3, all divided by 15. Later, when we'll tackle the factoring module, we'll see that we can factor a common factor of 5 from both terms in the numerator, and that will allow us to simplify. But for now, we'll leave the answer as I've written it here. All right, we've got one more example. Again, we're asked to rationalize the denominator. So I'm looking to multiply the top and the bottom of this fraction by the conjugate of the denominator. I want to multiply it by the conjugate so that I remove the radicals from the denominator. I'll keep the first term the same, so that's negative root 3, and rather than positive root 2, we'll subtract the square root of 2. If I multiply the denominator of the fraction by negative root 3 minus root 2, of course, I have to multiply the top of the fraction by negative 3 minus root 2 as well. Again, it might help you to include those binomials in brackets so that you can clearly see what you're multiplying. All right, in the numerator, I have 2 root 2 times negative root 3, so we get negative 2 root 6. 2 root 2 times negative root 2 will give us negative 2. Root 2 times root 2 is just 2, so negative 4 ultimately. Those are just the first two terms. Now we'll take the square root of 3 and multiply it by negative root 3. So overall our term will be negative, and root 3 times root 3 is just 3. And then finally the square root of 3 times negative square root of 2 gives us negative square root 6. Let's tackle the denominator. This is where we should eliminate our radicals. So we have negative root 3 times negative root 3, that gives us positive 3. Negative root 3 times negative root 2 will be positive root 6. Positive root 2 times negative root 3 will be negative root 6. And finally, positive root 2 times negative root 2 will be negative 2. We can simplify the numerator and the denominator. In the numerator, I see that I have negative 2 root 6 minus 2 times 2, so minus 4, minus 3, and negative root 6. So negative 2 root 6 minus root 6 is negative 3 root 6, and negative 4 minus 3 is just negative 7. In the denominator, I have 3 plus root 6 minus 2, so the middle two terms cancel, sum to 0, and 3 minus 2 is just 1. Because the denominator is just 1, and you'll find the same thing happens if the denominator is just negative 1. It's just that if it were negative 1, we'd have to deal with the negative sign somewhere. So if the denominator is just 1, we don't need to write it. So as a final answer, we can write negative 3 root 6 minus 7. Sometimes it's preferable to write the term without the radical first, so we could write this as negative 7 minus 3 root 6. And we're done.